Hi, everyone. My name is John Cypress. Right now, I'm a TA for the chemistry department, winter quarter 2023. So this series, we'll be going over the discussion worksheets for Dr. Farhad's class. Right, keep in mind, discussion attendance is mandatory. You still have to attend even if you're watching these videos. Okay, these are just supposed to be supplemental in case we did not finish, in case you would like to review them, in case you want to review them in advance. But these are supplemental, not a replacement for actually going to discussion. All right, so let's start on this worksheet. So this should say week 1 worksheet, not week 2. Now, the first question is regarding significant figures. So, right, there's 3 rules to significant figures, right? So the 3 rules right, if something is a significant figure, is first, if it is non-zero, right, it is significant. 2 is if it is a trailing zero in the decimal portion, right, only the decimal portion. Right, only the decimal portion. And rule 3 is if it is a 0 between 2 other sig figs. Right, so it's a significant figure if it's not a 0, if it's a trailing 0 in the decimal portion, or if it's a 0 between 2 other sig figs. Right, all other zeros are insignificant. Okay, so we're going to start with number 1. Right, number 1 is 5.40. So first we have 2 non-zero numbers here. Right, and is that last 0 significant? It is, because it is a trailing 0 in the decimal portion of the number. Right, so it is a significant figure. So this one has 3 sig figs. Number 2, 210, right? We have 2 non-zeros here. That 0, though, is not in the decimal portion, right? So we only have 2 sig figs here. For number 3, right, 801.5, we're going to count these non-zero numbers first, right? And that 0 is between 2 significant figures. It's not in the decimal portion, but it is between 2 sig figs. So this is also a significant figure, which means we have 4 sig figs here. Number 4, right, we have 1 non-zero number here. Now, all of these zeros are not in the decimal portion, right? These are in the integer portion of the number. So we only have 1 sig fig here. Number 5, we have 3 non-zero numbers. So those are 3 sig figs, and then we have to count the rest, right? So these are trailing zeros, the zeros at the end of a decimal portion. So those are also sig figs. And these zeros are also smushed between the ones, right? So those are also sig figs. So that is 7. This last one, 1.2. We have 2 sig figs, right? We don't look at this times 10 to the third. That just tells us the magnitude of the number, but does not tell us the sig figs for the number. Okay. All right, so 7. It says, why are significant figures important when taking data in the laboratory? Right, the reason they are important is they indicate a degree of precision. Right? When you write down the sig figs, it tells you how precise your measurement is. Now, we're going to go to the next question here, which will make more sense with number 7, with our answer. So it says, using 2 different instruments, I measured the length of my foot to be 27 centimeters and 27.00 centimeters. Explain the difference between the 2 measurements, right? 27 0.00 is centimeters, is more precise than 27 centimeters. Essentially, what this means is that you know that it's 27.00, right, to the 100th decimal place, versus the 27 centimeters, you don't really know. You know, like from your instrument, right? It says it's 27, it's close to 27. But it's not as exact, right, as the other instrument. So 27.00 is more precise, right? 27 is less precise. Now, these are the same number. So when you're doing like just math calculations, right, addition, subtraction, functionally, these are the same, right? But when it comes to taking measurements, right, and considering sources of error, things that may have been inaccurate, right, these are not the same. So same numerically, not really same in practice. All right. So number 9, it says we have these two equations and then we want to get the sig figs. So we're going to want to get the sig figs at the end here. So the rules of addition and subtraction without any division, right, is you're going to take, let me actually write these out. So for addition and subtraction, right, the rule is take the same number of decimal places as the number with the least amount of decimal places. So if one has 3 decimal places and one has 2, right, you're going to round your sig figs to the 2 decimal places. Now for multiplication and division, right, the rule is going to be your final answer, and that's also true for this one. I should scooch this over. This is for the final answer. Right. Same thing here. So for the final answer, you're going to have the same number of sig figs as the number with the least sig figs. So if you're multiplying 2 numbers, right, one has 2 sig figs, the other has 3, you're going to take 2 sig figs. You want the least amount of sig figs. All right, next, we have this problem. So what you want to do is make sure you round at the end. Right, you don't want to round in the beginning because you can get calculator error. So essentially, right, the end result, we're going to be using multiplication and division. So let's go ahead and see which one has the least number of sig figs. So on the top, right, we would have, let's see, 3 decimal places, right? That's where we would stop because this one has 4, and we're taking the least amount of decimal places when adding these. So we'd have 3 decimal places with an 8 out front. That would be what, 4 sig figs. Then over here, right, the least amount would be 2 sig figs. Sorry, not 2 sig figs, 3 sig figs. Oh no, sorry, two sig figs. Right, we have 2 down here, which correlates to 2 sig figs, right? This 1.02 has 3 sig figs, the 13.4 has 3 sig figs. So we're going to round to 2 sig figs at the very end, right? So what I would do, quite honestly, is I just plug this all into the calculator in one step and then round to 2 sig figs here. All right, so you round to 2 sig figs and we should end up getting 0.58. Okay, again, we're basing this on the least number of sig figs, right? Because we're doing this division at the end. All right, over here, we're going to be doing the same thing. Now, this is all multiplication or division. So I'm going to just count the one with the least number of sig figs. So this first one, you have 4 sig figs. The second one, you have 2 sig figs. This one, you have 4 sig figs, right? These last ones. On the bottom, you have 2 for this first one, and you have 3 for the other one. So overall, the number of least sig figs, right, with this whole problem with multiplication and division, is going to be 2 sig figs. So we're going to round our answer to 2 sig figs. So 432.7 times 6.5 times 0.2300, 62 times 0.103. All right, so with 2 sig figs, you should end up getting 1.0. Again, we're not basing this on decimal points. Number of sig figs for multiplication and division. Right, if it's just addition and subtraction, then you look at just the decimal points. But for multiplication and division, you're going to look at the total number of sig figs. Okay. So let's go on to the next one here. It says convert into scientific notation. So the way I like to do this is I like to put a decimal point right after the first non-zero number. I think that is easiest. So put a decimal point after the first non-zero number. That's where it's going to go, right? You're going to put the decimal point here after it's in scientific notation. So I put a decimal point here. I'm going to count 1, 2, 3. So I'm going right from this decimal point. I'm going forward, right? 3 places. This is less than 1, right? So we're going to get 9 times 10 to the negative 3, right? The negative 3 makes it less than 1, right? Negative 10 to the negative 3 is dividing by 10 cubed or 1,000, right? So the negative exponent just puts it in the denominator, right? You're dividing. So this is technically 9 divided by 10 cubed. That's why it works out to be smaller, right? Instead of bigger. All right, so if you're to show this with 2 sig figs, right? In the original problem, we can only do it to 1 sig fig. But if we were to do it to 2, if we had an extra 0 at the end, we would have 9.0 times 10 to the negative 3. Okay. Next, we have 23, right? I'm going to put a decimal point right after that first non-zero number. And the decimal point we currently have is right here, right? It's after the 3, right? I don't want to say 23.0 because that's not the correct number of sig figs, but the decimal would be there, right? After that 3, where it actually is. So I'm going to have to move this decimal right forward. So I'm going to have to multiply 2.3 times 10 to the first power, right? I'm kind of looking at where I want my decimal to be or end up, right? In this case, after the 2 to where it is right now. So for this first one, I put it after the 9 and I'm moving back 3. So negative 3. In this case, I want it up here, but I'm moving forward 1 to get to the decimal point. So it's 10 to the positive 1. If I were to do this with 3 sig figs, right, I would just make this 2.30 times 10 to the first power. You just leave it as times 10. Okay. So that is it for scientific notation. Next, 12, it says convert 4.66 centimeters to miles. There are 0.6 miles in a kilometer, right? So most of us do not know how to directly convert from centimeters to miles. However, they do give us a conversion factor here, miles to kilometers, right? So we want to go from kilometers to miles in this case. Our end unit is going to be miles, right? That is the end unit. So I start with 4.66 centimeters. Now you're going to see me always put this over 1. It's just because I like to do that. It just makes it look nice when you're horizontally multiplying. So 4.66 centimeters times what, right? We have 0.6 miles in a kilometer. Now, can you convert directly from centimeters to kilometers? Right, most people can't. Yes, you can if you do know how to, but most people cannot. Right, so what you want to do first is go to the unit of meters. That's easier to work with. So we know that there are 100 centimeters in 1 meter, right? That's 10 squared. If you're writing it like that, it's the same thing, right? The centimeters cancel out. Now I want to go from meters to kilometers, right? Because I'm going to want to convert kilometers to miles. So I know that there's 1,000 meters in 1 kilometer, right? Another way you could write this is 10 to the negative 3 kilometers in 1 meter. It's the same thing mathematically. All right, we get those meters crossed out. And then we have to convert from kilometers to miles, right? There is 1 kilometer and there are 0.6 miles for every 1 kilometer. And those cross out. I should do some blue. All right. So now you just go ahead and multiply this all on your calculator. Right? 4.66 times 0.6 divided by 100 times 1,000. And I end up getting 2.7, or let's do 80 miles. And that is your answer. All right, I guess the question can be, when you're converting, how many sig figs did you use? I'm sticking with this. I'm assuming that this 0.6 is an exact conversion, so I don't have to worry that there's some decimal cutoff, right? That's like not 0.6123, it's just exactly 0.6. So I'm going to stick with the original number of sig figs. Okay. The full number here, if you're calculating, is 2.796 times 10 to the negative 5th. All right. So 13, it says convert 556 degrees Celsius to Kelvin. Right, all you have to do is add 273.15. So to convert from Kelvin to Celsius, sorry, Celsius to Kelvin, you add 273.15. This is 829.15 Kelvin. And if you're going the opposite way, right, from Kelvin to Celsius, then you subtract. All right, next is 14. It says you want to convert 68.4 inches into centimeters, right? You should know the conversion between inches and centimeters by heart. So I'm gonna write down here. Right, we start with 68.4 inches. Now, if you do not know the conversion by heart, it is this. There are 2.54 centimeters in 1 inch. So we can use this conversion factor. This is 2.54, oops, wrong spot, 2.54 centimeters in 1 inch. Right, the inches cancel out. If I kept it as I did a second ago, right, then you would get inches times inches on the top, which is what you don't want, right? You want the unit to cancel out. So this is 68.4 times 2.54. You end up getting 173.736. And then I'm just going to round this to 3 sig figs. All right, B. All right, B says you have 1.85 gallons, right? And you want to convert this into decimeters cubed. So how do you do it? Right, what you want to do is this. You start with your gallons and you're given a conversion, right? You're given the conversion from 1 gallon to 3,785 milliliters. Let's do that first. So in 1 gallon, I want that to cancel out. I have 3,785 milliliters. Now, the conversion that you should know is this. You should know that 1 milliliter is equal to 1 centimeter cubed, right? So we're going to use this conversion to convert from a milliliter or liter type of unit, volume unit, to a length squared type of unit, sorry, length cubed type of unit. So we know that 1 milliliter is 1 centimeter cubed, and those milliliters cancel out. So now that I have this conversion, right, I want to convert from centimeters cubed to decimeters cubed. Now, I don't know off the top of my head. I do, but if you don't know off the top of your head, right, from centimeters to decimeters, what you can do is convert from centimeters cubed into meters cubed, right? So I'm going to start like this. For every 100 centimeters, I have 1 meter. Now, this is not the correct unit, right? I want centimeters cubed. So what you're going to do is cube the top and the bottom here. Make sure you cube the number with it, right? It's 100 cubed times centimeters cubed. It's not 100 centimeters cubed. That is where you will make a mistake on a test or on problems, right? Make sure you cube the number with it. Okay. Now we're going to go ahead and convert from meters to decimeters. So for every 1 meter, there are 10 decimeters. And now we're going to cube it again, right? So cube the top and the bottom, right? The number with it. You'll find that the meters, I'm not going to cross everything out, but the meters, the cubed, the centimeters cubed all go away and we're left with decimeters cubed. So in the end, go ahead and multiply this all out. You end up with 7.00. I'm just using 3 sig figs because we started with 3. So 7.00 decimeters cubed. That should be your answer. So here, 7.00 decimeters cubed. All right, so we're going to go to the next problem here. 15, it says, which has a greater mass, right? 3,245 micrograms or 0.00515 milligrams. What you want to do before comparing these is make them the same unit, right? So most people don't know how to convert directly from milligrams to micrograms or vice versa. So we're going to put these both in grams. So 3,245 micrograms. I'm going to convert this into grams. I know that there are 1 million micrograms. Just going to have to memorize it for every 1 gram. And then let's go ahead and convert this. So it should end up being 3.245 times 10 to the negative 3. Just want to double check here. Oops. Yeah. So this is 3.245 times 10 to the negative 3 grams. Over here, I'm going to do the same thing with milligrams. It's 0.00515 milligrams. I want to convert this into grams. I'm actually going to go ahead and write this in scientific notation. You'll see why in a second. This is 5.15 times 10 to the negative 3 milligrams, right? Those are the same. And I'm going to convert this to grams. So I know that there are 1,000 or 10 cubed milligrams for every 1 gram. Right? The reason I did this is just to make the math a little easier to plug in. Right? The milligrams cancel out. Your rules of exponents state that if you have the same base, right, you can just add the exponents if it's multiplication, subtract them if it is division, right? So x squared times x is 3, right? X squared divided by x is x to the first power, 2 minus 1. So this is 5.15 times 10 to the negative 6 grams. All right, now we're going to compare these two, right? We can see that this is bigger than this, right? It has a less negative exponent. It's a bigger number. So 3,245 micrograms is bigger than 0.00515 milligrams. And that is it for this problem for number 15. For this next problem, right, we're going to convert from Fahrenheit to Celsius. So the formula you can use is the degrees Celsius is equal to 5/9 of degrees Fahrenheit or times degrees Fahrenheit minus 32. Right, you can go the other way. So if you remember one formula, you can get the other just algebraically. So if you wanted the Fahrenheit formula, you just isolate Fahrenheit, right? Multiply both sides by 9/5, and then you can go ahead and add 32. So, all right, so we're just going to use this formula. We're really just going to plug it in here. So for 118 degrees Fahrenheit, right, the degrees Celsius is equal to 5/9 times 118 minus 32. 5/9. And we end up with 47 point, you can keep 2 sig figs here. I'm just going to write 2 decimal points. 47.78 degrees Celsius. And then for this other one, right, for 17 degrees Fahrenheit, we have 5/9 times 17 minus 32. Can you just plug that in your calculator? And we end up getting negative 8.33 degrees Celsius. Right, so this one you're just plugging and chugging into this formula. So that is it for that. To convert these both into Kelvin, right, all you have to do is add 273.15. So 47.78 plus 273.15. You end up getting 320.93 Kelvin, right? And then for the other one, right, for negative 8.33 degrees Celsius, you're going to just add. So negative 8.33 plus 273.15. equal to 264.82 Kelvin. And that's it. All right, number 18, right? It says calculate the mass of a block of iron where D is equal to that, the density, with dimensions of that, right? So first things first, right? We're going to be using this formula. D is equal to M over V. Now, just as a heads up, you may often see this density written as that, as a rho. Those often mean the same thing, right? We typically use rho in engineering and physics and higher level chemistry, right? Because D stands for derivative. So typically you're going to see rho if you take those courses, right? But in this case, we're going to stick with D. Rho also stands for density. And let me write that down. Right, so rho is also common. Those are the same thing, though. I'm going to stick with D for density, though. So in this problem, right, we have D is equal to M over V. Now, something that is helpful is to write down everything that you have. So I know that my density is 7.86 grams per centimeter cubed, right? I know that my volume is what, right? Your volume is length times width times height for a block, right? For a cube or a rectangular prism. So length times width times height, right? This is going to be 58.8 centimeters times 6.74 centimeters times 3.73 centimeters. All right, so I'm going to just multiply this out. Now, something I do recommend, I'm going to show two different ways here. You're going to want to keep all these decimal places. And this is in centimeters cubed, right? You want to keep all the decimal places so you don't make rounding errors at the end. At the end, we're going to use 3 sig figs, right? And the mass is a question mark. So all you have to do here is plug in the numbers, right? 7.86 grams per centimeter cubed is equal to the mass, which we're looking for, over the volume, which is 14.78, or whoops, 14,078, 1,478.24376 centimeters cubed. You end up getting the mass, once you multiply this out, to be 11,618.99595. Right now, we're going to just round this to 3 sig figs, since that's what we start with. Each of them had 3 sig figs. You take the least amount of sig figs for multiplication. So we're going to end up with 11,600. Oh, and this is in grams. Right, you'll find that these centimeters cancel out over here and here. The other way you can do this in the way that I think it is vastly preferable for most things with math is to solve this algebraically first, meaning don't plug in numbers until you have an expression. So if I were to start and do it over here with D is equal to M over V, and I wanted the volume, right? Or sorry, the mass. If you want the mass, you're going to multiply both sides by the volume, right? It's just algebra. You can cross out those variables, just again, like you would in algebra. You're just isolating one thing in the equation. It's just in terms of variables, there's no numbers. So it probably a little bit new doing this, but it makes everything so much easier. So you end up getting M is equal to density times volume. Makes sense. It's exactly what we did, except with numbers. And now when you plug in everything, you don't have to worry about so many numbers and writing them all down, right? So you get 7.86 grams per centimeter cubed, and then you could actually just leave the volume as what we had it in the dimensions, right? 58.8 centimeters, and then so on. And then you end up getting the mass to be equal to that, right? You're going to get the same thing. It's vastly preferable. You'll see in the future why. And I think the next two questions or the question after, it's just easier to not write down so many numbers all the time, right? And then you also don't have to worry about your units as much, right? You should still worry about them. You should still know that if you're multiplying grams per centimeter cubed times centimeters cubed, you're going to get grams, right? You should still keep track of that. But now you don't have to do the kind of mental gymnastics of canceling out all the units, right? It's a complex fraction with units, like maybe you have grams per centimeter cubed over, I don't know, centimeters squared per gram or something, right? You don't have to worry about it anymore. Solving for algebraically puts your units in check, assuming you did everything correctly and use the right formula. So I'm going to be using that method. I know most people are comfortable with plugging in numbers. It's just too much number plugging in. So I'm going to start solving for this algebraically and then just plugging in at the very end. All right, so 19, it says calculate the mass of a cylinder of stainless steel with that density with a height of 18.35 centimeters and that radius, right? So we're trying to find the mass again. So as we just solved for over here, mass is equal to density times volume, right? E is equal to m over v, or mass is equal to density times volume. All right, now I'm going to go ahead and write down all the things I have. So D is equal to 7.75 grams per centimeter cubed, right? We know that the volume has to be equal to, this is for a cylinder, right? It's the area of the base, which is a circle, which is pi r squared, times the height, right? Base times height, essentially, for these simple geometric shapes. So prisms and cylinders. Now we can go ahead and plug in the numbers here, right? We know that the radius is 1.88 centimeters. We're going to square that times the height, which is 18.35. And we don't know what the mass is, right? So we just have to plug this into M is equal to density times volume, right? We algebraically solved for it already. And I'm putting D times V. I just want to make that clear, right? dV, again, you're going to see that stand for stuff like differentials in the future. So D times V, not dV. Okay, so we go ahead and plug this in. Yeah, 7.75. This is grams per centimeter cubed. Again, times volume, which is pi times 1.88 squared, centimeters squared. And then times 18.35. And I forgot to put centimeters here. All right, so that ends up giving us centimeters cubed in total. So we end up getting M is equal to 1,579.08. I just rounded, but now we're actually just going to round to 2 sig figs here. So, or sorry, 3 sig figs. So 1580 grams. And that's your answer. So again, for this next one, this is where algebraically solving for it is very helpful, right? I'll show you why. So again, we're going to start with density is equal to mass over volume. Now, in this question, it says the density of aluminum is that a square piece of foil has 22.86 centimeters on a side and is found to weigh 2.568. So if you have a square piece of foil, right, for any square, the sides are all equal. Right, that's how a square is defined. So we know the length and the width, right, of this very thin, it's still a prism. It's not a flat piece of foil or an infinitely flat piece of foil, right? It is still has a height, very small height, albeit, but still has a height. So what we're going to do is this. We're going to start with the density. We're going to write down what we have, 2.70 grams per centimeter cubed. Now the mass is equal to 2.568 grams, and the volume is equal to length times width times height. Right? So we have the length and the width, right? You know that the length is 22.86 centimeters. You know that the width is 22.86 centimeters. What about the height? Right, the height is actually what we are looking for. What is the thickness of the foil? So I'm going to still leave this as h. Right, now I can see that h is the variable I want. You do not see h in here, right? You just see volume. So the way you can solve for this algebraically, because I don't want to plug in a bunch of numbers, is we can say that density is equal to mass over length times width times height, right? We have all those quantities except for height. And then we're going to solve for height here, right? What you do is multiply both sides by length times width times height, right? You end up getting length times width times height times density is equal to mass. And then you end up getting the height, which is what we want, right, is equal to mass divided by length times width times density. Right, so I can plug it into this formula. Again, you can plug in your numbers into the density formula. You'll find that height is the only thing you don't have. I just prefer not to plug in a whole bunch of numbers and have a whole bunch of decimals to keep track of. So I do it at the end. So we have this formula. The height is equal to mass over length times width times density. Now we can just plug everything in. 2.568 grams over, and this is length, so 22.86 centimeters times the width, which is the same thing, 22.86 centimeters. And then times the density, which is 2.70 grams per centimeter cubed. You go ahead and plug this into your calculator. And you end up getting, and use 3 sig figs here, 3 sig figs because of the density. 1.82 times 10 to the negative 3 centimeters, right? If you're looking at your units here, the centimeters cancel out except for one unit of it, right? So you get these two go away, then this becomes centimeters to the first power. The grams cancel out. Your unit is 1 divided by 1 over centimeters, the complex fraction. You can rewrite it, right? You get centimeters in the end. So now that I have this is almost my answer, right? We want the answer in millimeters, not in centimeters. So I'm going to go ahead and convert this. This is 1.82 times 10 to the negative 3 centimeters. I like to put it over 1 times then we're going to go ahead here. So 1.82 times 10 to the negative 3 centimeters. I'm going to convert this into meters first, just because I think it's easier. So there's 100 centimeters in 1 meter and squared. And then there are 1,000. I'm just going to keep this as 10 cubed, 1,000 millimeters in 1 meter. And most people don't know the conversion from 2 different base units, or sorry, smaller units. So I'm going to meters first, right? There is 10 millimeters in a centimeter, and you can also use that conversion if you don't know. It's not to worry, right? You can do it like this. So we go ahead and plug everything in. And you can actually just use your rules of exponents here. So you end up getting 1.82 times 10 to the negative 1 millimeters. And that is your answer. All right, and that's it. So again, for this problem, it can be helpful to write everything that you have. It can be helpful to write algebraically, so you don't have to have so many decimals everywhere. That's how I recommend doing it. All right, you just can plug it all into one step and be done. All right, 21 says adding water to a beaker of water will not change which of the following: the moles of water, the volume of water, the density of water, all the above. Right, the density of the water does not change. Moles does change. Right? Moles is just a unit quantity. I'll talk more about this in the next worksheet. So it's like you have a dozen of eggs, you have 12 eggs, right? You have a mole of something, you have 6.022 times 10 to the 23rd of something, an Avogadro number of something, right? So you can have a mole of eggs, right? It's just 6.022 times 10 to the 23rd. I don't think that many eggs exist, but a dozen of eggs is 12. A mole is that many, an Avogadro number of something. Right, a half dozen is 6, a couple is 2. It's just mole is used to describe an amount. It's just of something, right? Just like couple, dozen, half dozen, so on and so forth. So the volume of water does change, of course, right? And then the density does not. The density will be constant. So that is it for this worksheet. I hope that helps. I will be doing the next worksheet, and I will see you there.